So we're interested in the manifold of all phi, which satisfy this nonlinear, renormalized, regularized PDE plus some smooth term. So that's a manifold in the space of functions, which depends on rho, and which you can think of either being dependent on psi or being a random manifold. So my typical picture was to look, for instance, at lambda equal to 1, where this is kind of a very, a subset of the space of all functions, which is a very high codimension, because after all, that's a pretty substantial constraint. And we were interested in kind of parametrizing this manifold, essentially by the manifold which we by the affine space or the linear space which we get from the in the absence of the nonlinearity, where we did choose by now we already know kind of canonically one solution. I mean, one solution of the linear problem. And then we're kind of looking at pi 0 plus p, and then we were thinking of lifting this this to the nonlinear case, thereby defining a parametrization from lambda p into phi. Let me also kind of add the h, or it's even nicer to put it in the other order, and so far we have been putting postulates on this parametrization, which make it unique, which allows us to come up with an algorithm, and the main idea was to write both as the counter term and the general solution as a formal series, where writing the general solution as a formal series makes the multi-indices appear. And therefore, in the end, the object we were really working on are these pi's, which we think of as being formal power series in the dummy variables, in these infinitely many dummy variables, with coefficients in the space of random space-time functions. And C was in R of Z3. And we were almost done. I think we were perhaps quite not done with the section where I told you that also C is unique. And the uniqueness of C relied on kind of a combination of a type of a condition we already introduced, we already worked with in case of the uniqueness to obtain the uniqueness of pi, beta, given pi beta minus. And in this case, it was a condition on the right-hand side, pi minus. Every component, it's averaging over a length scale r, which here we let go to infinity, evaluated at the origin, and I have to put the right beta factor here, which is 2 minus the homogeneity of beta. R goes to infinity. So this should be less than infinity. That was a postulate which was well motivated, at least when the regularization goes to 0 by scaling. And in fact, the only way we use it is by saying that a certain space-time ensemble average vanishes provided the homogeneity is less than 2. And this was complemented by a population condition or by a sparsity condition on the C, which reads that we say Ck of Z is equal to 0 unless, so unless means if not, Sk is less than 1. And that was, so the right way to, to make the connection, it really comes up in this form, and that's the same 2 here. And this here will be identified with some homogeneity. And so that is the last piece that I wanted to say something. I waved my hands and I said this is BPHZ, which is kind of jargon from mathematical physics. And but let me give you a little bit of more detail on this. And because it's important, it's in a certain sense perhaps one of the crucial points that after all we were, the most mysterious part in what we're doing is this counter term. So the fact that we have to fuss with the equation, that we have to change the equation, and by this ansatz here, the counter term is really determined by these constants Ck. So understanding why the constants are in fact determined, unique, why there's no degree of choice left is, in a certain sense interesting or crucial for this problem. So let me be a little bit more specific and give you some more details. You'll see it kind of spelled out a bit better in the lecture notes. I think this morning there should be a kind of a new version of it, which now is 21 pages long. So, so the reason for this is that there are 4 classes of multi-indices beta in this problem which have homogeneity less than 2. And what's the significance of 2? 2 is the order of our differential operator. And so that's the reason why 2 suddenly kind of plays a role. And those are, let me enumerate them. So there is the class of multi-indices which are just a multiple of the entry 3. There is the class of multi-indices where I add a del 0. So 0 is, this 0 is a space-time 0. And then there is the class of multi-indices where I add twice this basic multi-index. And then there is the class of multi-indices where I add a kind of a non-trivial space-time index, in this case just spatial. And EI, so EI is a special case of an n where you put zeros besides in the ith position. So it's a Cartesian unit vector in space-time. And and those are there are only 4 classes. Those are all the classes of multi-indices which are less than 2, length than 2, and that has to do with kind of this formula here, which I mentioned before. And in fact, just as an exercise, what are the homogeneities here? So in this case, it's -1 plus 2sk 2k plus 1 times s. Here it's 2k times s. Here it's 1 plus 2k times s. And in the last case, it's 1 plus 2k plus 1 times s. So that's just, you see just this from kind of plugging in this formula. And this here is the same expression which comes up here. And in fact, this class 2 is kind of special. And that's what I want to explain a bit. So that has to do with the symmetries we're imposing. So, for instance, let's look at a moment for the classes 1 and 3. So we always assumed, or something we did on the first day, we assumed parity, which means that the noise is invariant in law under switching the sign. And now by the uniqueness result we have on pi, this transmits to the model, and we find that minus 1 to the power 1 plus n beta n pi beta is the same as pi beta, and this holds. So you first get it for minus. Beta equal to 0 is just a reformulation of this. And then by induction in this quantity, going through the definition of the model, you see that it kind of can be propagated by an inductive argument. And in fact, it holds both for the positive part and the negative part of the model. And this in turn implies that the expectation of pi minus r at 0 vanishes for the classes 1 and 3, but not for 2. And this was ultimately the reason why we don't need a counter term. Of the form h rho times phi square or h rho times 1. This is something I said in the very beginning, and now you kind of get a kind of a more advanced view on this, that indeed these counter terms would arise from, you would have to put them in order to ensure this vanishing condition, or at least this limiting vanishing condition, for multi-indices 1 and 3. But since we assume this parity, since we make the symmetry assumption on our noise, we don't need them, which is something we kind of argued in favor of earlier in a kind of much less detailed way. And the same thing is now, if you look at the class 4, that's related to the reflection symmetry, which was that if I flip the ith spatial coordinate and I impose that my noise is invariant under this, and white noise would have this property, then I get something very similar, where here we have a different expression which governs the sign, and that ultimately is related to the fact that no counter term of the form hi rho di phi is needed. So in principle, it would be an exercise to look at a situation where you allow for a noise which does not have these symmetries. In this case, you would have to make a richer ansatz, you would have to include these three, or 1, 2 plus d, so d plus 2 counter terms into your ansatz. That means the model would get more complicated, but in principle you could proceed very much the same way. But for simplicity, and since this is anyway the symmetries which are satisfied by white noise, we don't do that. Okay, so that's the first remark. Now, why uniqueness? So let me erase the symmetry thing here and see where's the eraser? Over there. Thank you. So why is the counter term fixed? You need a kind of an inductive argument. Over the multi-indices in the 3 component, and it relies on a triangular structure which is revealed by the formula we have for pi beta, which was delta 3 plus pi 1 plus pi 2 plus pi 3 is equal to beta, pi 1, pi 2, pi beta 3, plus beta 1 plus beta 2 is equal to beta, c beta 1 pi beta 2 plus del beta 0 times xi. So looking at this expression, you figure out that pi beta minus depends on pi gamma only for gamma 3 less than beta 3. So only prior models enter the definition of pi minus. So that's kind of an inductive property which allows you to construct the model. So that's good. And that's just due to the fact that we have del 3 sitting here, and due to the assumption that beta 1 of 3 has to be larger than 1. But now for us more relevant is how does it depend on C gamma? And there it's not so good because, or CK, or CL, because the borderline case may happen. So that's not good enough for an induction, but luckily we have a better property for multi-indices of this form. So if we look at the special case where the beta is of the form or of the class 2, then we're in a better situation. Then this depends on CL only for L strictly less than K. So that's good. That's bad. And that's good. And this allows us to run an induction where an induction in K, where we first treat the second case and then the others. And the second case is done by the following very plain observation, namely that, this is not quite correct. I have to, this is only true if I take off CK. And the reason being that I have here always this term when pi 2 is equal to del 0, which is contained in my beta, and pi 2 of del 0 is just the unit, it's just the constant 1, in which case I get CK. So only if I subtract CK from pi minus do I get this triangular structure. So again, this looks bad. So this is bad, and this is bad. But now comes our assumption, because by the postulate we have that Ck can be written as the limit of r goes to infinity of the expectation of pi k delta 3 plus d0 minus Ck averaged and evaluated at 0. So this is a trivial observation. Ck is a deterministic constant, so it's oblivious to the averaging, it's oblivious to taking the expectation. So this cancels against that. And then we're left with exactly this assumption here in the case where the homogeneity of this coefficient, which is given by this expression, is less than 2. So by our postulate, we do have this. So now you see the induction. You're at level k. You first go to this multi-index. You determine Ck by this condition. This involves this expression, but this expression here only depends on things which are already which have been fixed by induction hypothesis. And then you move to the other cases. It doesn't matter in which order. You'll always be fine because now you know Ck, so that's not a problem, and the rest is by induction. So that's that's a typical argument. So in a certain sense, this theory is full of kind of these triangular structures and induction arguments. And this is the first time it really comes up at a crucial place where you realize that indeed the counter terms are determined. Okay, so questions? Yes?
So how can you determine Ck by this limiting formula if Ck also is the right side of the equation?
Okay, so first of all, you have to accept the formula as such, which follows from the postulate. And then you're right at first glance that this looks like cheating. But now this expression here, that's this statement. If I subtract the Ck, so if I look at this here in its own right and I kind of look at this, I realize that it does not depend on Ck anymore. It just depends on CLs with L strictly less than K. So therefore, this expression here is fine by induction hypothesis. More questions? Okay, good. Right, so now that means we have dealt with the now everything is fixed. So we really have constructed this map, at least in this term by term way, in this term by term fashion. And now the last thing I have to tell you are some bad news. And the bad news is that this map is not really canonical. And so it's kind of completely fixed, but it's, if you want, Eurocentric. It does see the origin. And that's unfortunate because that means it's not, it's not canonical. It's not really natural. It's not universal. And this is something one has to deal with. But again, kind of general principles of geometry, I think, perhaps in a certain sense, due to Felix Klein, come to your rescue. I mean, like in so the general principle of geometry is, if in a certain sense, like in affine space, you don't have an origin, that begs you to kind of understand your geometry by looking at the group of all transformations, in this case, all affine transformations. And that's exactly what's done in regularity structures. So there is some non-universality in this construction of what Heira calls the model. And instead of giving up and saying, okay, that's bad, let's stop, the right attitude is to say, okay, there is this non-universality, so that means I don't just have one model, but for every base point I have a model. And then I should understand how these models transform. So I should look at kind of a transformation group which comes with this structure. And that transformation group is what Heira calls, or what perhaps already before him was called, a structure group. And that's so there is a certain kind of a symmetry group related thing which emerges, which carries a lot of information and which is an integral part of this parametrization. So that's what I want to explain next. So that means it will still get a little bit more algebraic, but in the end there is a very clear geometrical idea behind this. And so let's revisit kind of the shift invariance of the manifold. So there was an observation which we did very early on, namely that if a couple of functions and right-hand sides, if this solves our equation, L phi is equal to lambda phi cubed plus h phi plus xi plus some analytic function, then of course, if we shift simultaneously the solution and the right-hand side, you still get a solution, right? That's a very basic, fundamental invariance, which has to do with the fact that these coefficients do not depend on space, time, and that's kind of a very important property because it fits well the kind of stationarity of the noise we want to consider, like white noise. So now you may wonder, is our parametrization compatible with this invariance? And this compatibility of our parametrization with an invariance was crucial when we looked at scaling. In a certain sense, we fixed our kind of our map, our chart, our parametrization by insisting that it's compatible with scaling. That was the guiding principle of making this construction unique, because that allowed us, gave us these scaling invariances in law, which were crucial in kind of fixing that structure. But in a certain sense, we did too good on this side, so that now on this side, we're in not such a good situation. So in fact, it will become clear that it is not true that our parametrization does not respect this invariance. It is not true that if we're given kind of a point on our manifold which has these parameter values, and now I'm including the right-hand side, then this does not imply that if I shift my parametrizing affine function, and if I shift my noise, then this is mapped on the shifted configuration. That's not true. And that's kind of very important to realize that while the analogous statement was true for scaling, it's not true for translation. So it's a little bit like, when you try to fix one, the other one doesn't work, and vice versa. But here the decision is to stick to what we did, and in a certain sense accept this fact here. And accepting this fact here means that you don't really have a single model, a single parametrization, but for every origin, you have a parametrization. So hence, we get a parametrization for every base point. I think that's language of regularity structures in time space, replacing the origin. And in that one you would define in the following way. You would say, well, let's look at a different parametrization of my solutions where I replace these coordinates, which were based on the origin. Remember that the origin was hardwired in this definition by defining the coordinates like this. So replace this by putting x here, which in a spelled out way means this here. So 1 over n factorial, the nth derivative of p now at x to the power beta n times pi x beta, which I can also write as the sum over beta z to the power beta, which are the original coordinates, but now applied to the shifted p, pi x beta. So the changes are here and here. Yeah? So it's just a new object. It's a new object. We use exactly the same cooking rule, the same recipe to define the same type of object, but this time with the origin replaced by another space-time point. So the picture you in a certain sense you should have in mind is that we have our nonlinear manifold, and now we have kind of different parametrizations. One's for the origin 0, and one's for the base point, the general base point x. And there are different ways of representing representing a point up there, which means that, of course, in a second we have to look at this nonlinear transformation of parameter space. So very much like in differential geometry, when you cover your manifold by different charts, that induces a transformation on parameter space on the underlying Rn or so. But here, of course, everything is infinite dimensional. So down here we have the analytic functions, and up here we have the general functions. And so that's what we're going to do in the next step. But let me just point out a couple of things here. So for instance, xp del n, when you take a multi-index, which, as we say, is purely polynomial, then this now is the space-time monomial shifted into this new base point. And so like before, you assemble all these coefficients into a kind of this object, this formal power series. So that means you put yourself onto the same space, which is convenient, and you define pi x minus very much the same way we defined pi minus. So this is Z3 times pi x cubed plus c times pi x plus psi times 1. So note that these things do not depend on x. So we should clearly the since the parametrization of the counter term doesn't see the p variable but just the lambda, c should not acquire an x. There is a universal the counter term is universal, but the parametrization of the solutions is not. And of course, the noise is universal. And then, of course, you also have that L pi x is equal to pi x minus up to a polynomial of the right degree. We postulated that to be the homogeneity of beta minus 2. And the last thing I want to say is that there is a tiny bit that's, after all, pretty well behaved. So because we have that for the multi-index 0, in which case this formula just reduces to psi rho. This is the same thing as pi minus 0. And by the uniqueness, by Liouville, this implies that pi x 0 is equal to pi 0. So this distinguished point here, well, I shouldn't draw it here, but in the this is lambda equal to 1. There's another plane which is lambda equal to 0. We have this distinguished point, pi 0. That's universal. That's a good thing. But the rest is not. Questions so far? So now, so this was in a certain sense just introducing notation. And now I have to tell you a bit more about this transformation of parameter space. Are you still with me? Otherwise, ask questions, because that's kind of really a core part of regularity structures, this change of base point transformation, the fact that you pass from one parametrization of your solution manifold to another parametrization. Yes?
Maybe it's a silly question, but so we're looking now at the equation after we transformed it with this hat thing that we had last time, or we're looking at the original?
So the hat was just a temporary notation to introduce the scaling operation.
Okay.
So that the hat was just something local notation-wise. That was in the context of still fixing this original model. And the main idea of fixing this original model, meaning fixing this map here, was to say that it should be compatible with the scale invariance of the solution. But the scale invariance is always, you single out a point, right? And in affine space, you don't have, there is no natural point around which to rescale. So that tells you that the construction we did so far depends on somewhat arbitrarily deciding one point is the origin for the scaling operation. And we could have taken any other point, and unfortunately, we get different maps. So the hat was just something local to kind of find a notation for this rescaling operation on the space of functions, on the space of right-hand sides, on the space of parameters lambda. But in a certain sense, you should forget the notation now. Yes?
I just have a question about the notation.
Yes.
There, the x0, the first x stands for base point 0, stands for the multi-index, right?
So this
Upper side.
upper side.
Uniqueness.
Yes. So I like to be lean in the notation. So here this pi is the multi-index pi equal to 0.
Okay.
When I don't put an x, then I mean kind of base point
0, 0, right?
origin
Okay.
0. Yeah. So that's true. I mean, I'm sometimes being very lean, borderline cryptic with the notation in the sense that I don't like to put too many indices. And of course, sometimes one has to think a bit and understand what it means, but you're exactly right in what you were saying. So here it meant multi-index equal to 0. Here it always means multi-index equal to 0. And base point equal to 0. So multi-index equal to 0, base point equal to 0, and so on. More questions? Yes?
So please go on. So you said the object you constructed before is not invariant with respect to the base point. So you introduce this new thing.
Right. So it's not. It's so the solution manifold, the object we want to describe, is perfectly invariant with respect to shift. That's kind of a very important structure of a PDE with constant coefficients. So the object we're after, the object we want to describe, has this invariance. But now, unfortunately, we found a parametrization which does not respect that invariance. That's what I wrote down here. So if you shift, so in a certain sense, we think of these. So the way we think about, our parametrization is we take our affine function, which is a perfectly smooth function, and then we crank on the nonlinearity. So we deform it into a solution of the nonlinear equation in some kind of continuous way. And so in a certain sense, the phi is somehow, you should think of the phi as being somehow close to the p, a deformation of the p to make it into a solution of the nonlinear problem. And now we did construct this in a unique way. I mean, I gave you in a certain sense, I gave you an algorithm of doing that. But unfortunately, this algorithm depends on the choice of the base point, because the algorithm, we kind of made the algorithm into an algorithm. We ensured uniqueness by the parametrization being compatible with scaling. And scaling inherently kind of singles out an origin, right? And so therefore, the choice of the origin is hardwired into this parametrization. Now, of course, there is nothing special about the origin, which means I can do exactly the same math. It's just, in a certain sense, relabeling with a different origin, which I call x. And unfortunately, that gives a different parametrization. So therefore, in a certain sense, you're forced to think about kind of a change of parametrization. There was another question?
I mean, it seems to me you view your construction try to respect the scaling invariance, and then it breaks the shift invariance, the parameterization. So
Exactly.
What if we do the other way? I mean, we try to make it respect the shift invariance first.
That's a good question. I don't think it works, because the scaling invariance was crucial to appeal to this Liouville principle, to this PDE principle, which gave us uniqueness.
So it's inspired by the PDE techniques.
It's inspired by this Liouville principle that in a certain sense, if you look at the difference of two solutions of the linear problem, it must be an analytic function. And if it grows at infinity less than a certain polynomial rate, it must be polynomial. And so if you have a certain vanishing order at the origin, it must be 0. So I don't know a substitute for this. So I don't know a way of kind of not using scaling. Yes?
I think if when you saw the proof of this theorem, we need to decompose P like a Lorentz series of Lorentz. When you decompose some function with the Lorentz series, you have the unicity of the coefficient. If all coefficients coincide, you have the polynomial. You have the uniqueness of the polynomial. So here you can. It's not possible to have the. It's not possible to have the invariance if the function doesn't coincide. So it's the principle of homogeneity function.
Yes. So, or another way of saying it is that if we were just interested in the linear case, we wouldn't have a problem. It would work. So if we kept lambda equal to 0, it would be perfectly possible to achieve both things at the same time. That's, in a certain sense, it's just the consequence of this here. But in the nonlinear case, we cannot, in general, achieve both. So that's a consequence of the fact that we're looking at a nonlinear problem. Yes?
Is the Q here a shift of P by X?
Here?
No, in the picture, the Q.
No, that's the point. So only if you were interested in the linear case, then Q would be just shifting P by X. But in the nonlinear case, it's more complicated. And that's exactly what we have to look at now. Yeah, so that's exactly, if what you said were true, then this here would be true. But it's not. Yeah, it's not that we cannot, that's exactly the crux of the matter. Q is not equal to P dot plus X. Only if this point lives in the affine part, then it's true. But as soon as you put on the nonlinearity, it's no longer true. And that's exactly what I wrote down here, not, once again, without drawing the picture. Yeah, that's a very important thing to realize, I guess. More questions? Okay, so now what's going to happen next is that we have to algebraize this. I mean, obviously, this picture defines a nonlinear transformation on the space of affine functions by associating to a point, to a configuration, to an affine function P. You associate the affine function Q by going through this picture. Yeah? So that defines a nonlinear transformation on the space of affine functions. And now the idea is very much like we algebraized this map here. By making this ansatz, we're going to algebraize, so to say, this nonlinear transformation by lifting it to a linear transformation. This old trick of lifting a nonlinear map by pullback to something that's linear. So, yes.
Maybe I understood now. So you take P, it's mapped to phi, and then you go back and see which Q would go to phi.
Yes, exactly. So it's really, I mean, I think, I don't know whether you've taken a class in differential, what's it called, kind of differentiable manifolds or differential topology. I mean, take the sphere, right? I mean, if you want to introduce coordinates on the sphere, you cannot use a single chart, right? So you have your sphere, and then you would have one charge which covers a patch of the sphere, and then you have another charge which covers another patch of the sphere. They have some overlapping, and this defines now a transformation on parameter space, right? And that's very much the same spirit, just that we're in infinite dimensions now, right? So this curved manifold now is an infinite dimensional one. But the spirit is exactly of that picture.
And the transformation will be nonlinear.
So like for the sphere, this is nonlinear, and this is also nonlinear. It's an infinite dimensional nonlinear, and actually just informally defined, because remember, this entire picture is informal. Informally defined nonlinear transformations of analytic functions. Yeah? Okay. So let's talk about this change of base point transformation. And that has a name. So I'm using the name of regularity structures. It's a gamma. X stands for the space point. You go from 0 to x, so I drop the 0 again. For a reason that will become apparent later, I think in terms of the dual. So therefore the star. So let me draw this picture again in a kind of a nice way. So here we have the space of P's. Here we have our solution manifold phi. Here we have the space of Q's. And we have these two different maps. One is based on the origin, and one is based on the base point x. And so that means if we take a P here, we're mapped via this here onto a phi, and then we're mapped back onto some Q. And this defines, informally defines, a map from lambda P to lambda Q, which I give the name P subscript lambda and X. Lambda X, right. So in the first coordinate, this map is trivial. And in the second coordinate, it depends on both. It depends on the first coordinate, and it depends on P itself. And of course, everything depends on the base point. Okay, so and it's done in such a way. We have this identity, beta z beta lambda p pi beta is equal to beta z beta lambda p lambda x pi x beta. That's what this picture means in formulas or in terms of coordinates. And so as I said, we don't want to work with this nonlinear map, but we, as it said, we pull it back to an endomorphism of our power series space. And we do this in the following way. So we take an element of our power series space. We define gamma star x applied to pi by saying how it acts on p lambda. And we let it act in the obvious way by having pi be applied to, other direction, lambda p lambda x. And the meaning of this is still, in a certain sense, an informal line, because I'm thinking of my elements pi as being functionals on the space of lambda p. Why is this at least formally a functional on the space of pi p? Because of the definition of Z3 of the definition of these things. Right. So if I didn't have a formal power series, but if I had just a polynomial in these variables, then for such a polynomial, I could stick in a function, and then I would get some algebraic, some polynomial expression in lambda and in the derivatives of p. So I could think of it as being a functional on this space. And if you allow me to think of it like this, I can pull back this nonlinear transformation by understanding how it acts on functions on the space, right? That's a construction which you must be I'm sure you have seen in the finite dimensional case, if you have a nonlinear transformation which goes forward, then you get a linear mapping on the functions of this space, which is pulled, that's pulled back. And then you can look at measures, which again is a push forward, the dual object. So there's always this nonlinear. It's this, old idea of lifting to something linear by going to a much larger space, like how you pass from classical mechanics to quantum mechanics. So this idea of that's a very common idea. And so this is the way to algebraize it, and there are immediately some nice properties you get of this operator. Namely, it's an algebra endomorphism. So it's an algebra endomorphism, meaning that if you apply it to the product of two elements in this space, it should be the product of the answers. And of course, the 1 is mapped onto itself. And moreover, the Z3 variable is kind of left invariant because the first component is completely trivial. And in fact, so let me see how I'm doing with time. I would like to, at least I would like today to state the main result before before the weekend starts. So let me see how am I going to manage this by kind of getting a bit short on some of the things here. So right, and this so now the important thing is that this relation here translates into a transformation rule. I can recover the pi from the pi x by applying gamma x star. And I can do the same thing, and that's a good exercise for the pi minus. So these linear operators, or these algebra endomorphisms, now kind of transform these elements of the algebra in this nice way. Now, why did I call it? Why did I give it a star? So the reason is, there's one intuitive reason, which is that pull back is always, in a certain sense, a dual operation, right? Forward with the nonlinear transformation, pull back is, in a certain sense, dualizing, because you look at functions. The more kind of the better reason is that there is in fact a pre-dual, and that one has also nice properties. Let me state this, and you'll find more details in the notes. So that's section 15. So gamma x itself, so without the star, acts by shift on the space-time polynomials. So what do I mean by this? So let me first explain this duality thing. So our space of formal power series in these variables is canonically dual to the space of polynomials in the same variables. And the identification, the canonical dual, is just via the monomial bases which you have in both spaces. And now notice that because we're in infinite dimensions, the dual space is much larger than the original space. So here I always mean algebraic dual. Right? That's the typical phenomenon in when you're in infinite space dimensions. The original space is infinite dimensional but small, namely all polynomials, and the dual space is infinite dimensional but large, namely all formal power series. So this is, I don't know how much linear algebra you did take. I didn't take so much myself, but it's the passage from a direct sum to a direct product. And in this vein, we can recover this map, in fact, as the algebraic dual of a linear endomorphism, no longer an algebra endomorphism, on this polynomial space. And then there's one realization. I mean, some of you over there asked in the first row all to the left. You said you asked this. No, let me give one last piece, namely that the space of space-time polynomials is naturally embedded into the space of polynomials in these many variables, so canonically. And this natural embedding is defined by saying, so take a space-time polynomial p. So it's not now an affine analytic function, but just a plain polynomial. And take an element from the dual space. So let's take a monomial. And let's specify how this monomial acts on p. And we just take our definition, which we have, which makes sense, which I can write down because p is a polynomial. So that means the polynomial space is canonically contained in there. And let me add this additional layer to the picture, which we had already before. So there is the lambda equal to 0 picture where our distinguished pi 0 is sitting. And of course, we also have, if we take a phi from here, we also have, the same map, which is, let me erase this. So for lambda equal to 0, we can look at this nonlinear transformation. So we can look at p is equal to 0 x. And that one is just the shift. So in the linear case, we're back to the shift. And that means, in this language, that if we take our pre-dual, gamma x, and we apply it to an element from this subspace, then the answer is just the shift. So on this small subspace, this nonlinear transformation acts as you would like it to act. But as you go nonlinear, you lose this property. That's one thing I wanted to say. Then what's going to be important is the matrix representation. So the nice thing about this pre-dual space is that it does have a basis, a canonical basis even, which is just the monomial basis. So it's indexed by multi-indices. Whereas the dual space is too large to have a countable basis. So that means gamma x has a matrix representation. And we even, so I call this gamma x gamma beta, where gamma and beta are generic multi-indices. And by kind of the nature of a basis representation, we have that the number of multi-indices for which this expression is non-zero is finite for all beta. And if we look now at the dual, which is just kind of switching the indices, we learn from this that we have a nice representation. So we can write the dual acting on some pi. Pi is now an element of the larger space. We can write this as a sum over all gamma, gamma star x beta gamma pi gamma. And because of this finiteness property, this sum is always effectively finite. So although you will often see sums over all multi-indices, which look like infinite sums, they're always algebraic in the sense that, in fact, they're actually finite. And then this observation I just made that gamma is easy on this subspace. So the gamma xp is equal to p plus x translates into the fact that gamma x star del m gamma is equal to m choose n x to the power m minus n, provided gamma is equal to delta m for some n, and 0 else. So some of these matrix elements we know quite well. Let me just mention two more properties. We have a kind of a sparsity. Also here we can construct the gamma in such a way that many of the indices are equal to 0. Let me just copy this. And we have a triangularity once more. Triangularities are extremely important. So, in fact, these gammas are triangular matrices, infinite triangular matrices with ones on the diagonal. And as such, of course, always invertible. And in fact, they form a group, and the group is called the structure group. But I don't need that. And the last thing before I can state the theorem, which I do absolutely want today, is that now we can go back to combining shift and scaling invariance. And what if I had more time, what I would explain, and perhaps I'm going to explain it on Monday, is that in the limit rho goes to 0, we did already convince ourselves that r minus beta pi beta r and r2 minus beta pi beta r minus should have laws which are independent from r. And in fact, something similar holds for this object gamma. In fact, r to the power gamma minus beta, so the homogeneity of gamma minus the homogeneity of beta times x times r times x, and I forgot the r here. This thing has beta gamma has a law independent of r. And so now, in the last 5 minutes, I can at least state the main result. So that would be section 2, main result and sketch of proof. So there is a paragraph 1 where I explain what estimates to expect. And perhaps I get back there on Monday, but it's essentially based on these limiting scale invariances. And now comes the statement. So, theorem. Okay, so that's joined with Luca Brooks, Markus Tempelmeier, and Pavlos Tsatsoulis, and myself. And it's, in a certain sense, a version. It's a boiled down version of a paper with Linares, in addition, or replaced by Luca. And the statement runs as follows. I will give you first kind of a simpler version. So suppose the ensemble of xi's on the space of Schwarz distributions Let's first look at the Gaussian ensemble. Suppose that the Gaussian ensemble on the space of Schwarz distribution satisfies the desired symmetries. So the symmetries which we had in the second paragraph, so that was shift symmetries, meaning stationarity, reflection. And I don't have to state parity because that's automatically satisfied for Gaussian. And we have an estimate in the sense that the variance of if I apply psi to some Schwarz function zeta is estimated by a norm. So let me first write it informally, by the h dot s norm of zeta squared. So that's a Sobolev norm of regularity S, and S is positive and irrational. So S is in this unit interval, as we've seen we should be, and it is irrational in order to apply Liouville. Then we have sorry, this is, if I write it like this, is minus S. So then we have, if we look at the at the model, and in the base point, the origin, without loss of generality. We mollified on scale R. We evaluated at some point x. We take the LP norm in probability. Then this is estimated by R to the power alpha x, or R plus x, to the homogeneity of beta minus alpha. We get the same type of estimate on the right-hand side, just that this exponent gets worse by 2 digits. And we can also estimate, and that will be a crucial part of it, this base of a change of base point transformation in the same stochastic norm. And this is estimated by the parabolic distance between x and the origin to the power beta minus gamma, or the difference in the homogeneities. And so we have this for any p less than infinity, any point, space-time point, any beta. And the constants depend on p. They depend on the s. They depend on the beta. They depend on the gamma. They depend on the mollifying psi only through its semi-norms. But they do not depend on rho. And of course also not on x and on, do I have anything in r? So this theorem gives estimates on what is called the centered model, pi, including its right-hand side and the change of base point transformation, estimates which are stable under removing the regularization, whereas the C's blow up. So that's exactly the sense in which I said that's exactly the main part of the task, which I said at the beginning, that we want to, in a certain sense, keep control of our solution manifold as we let the regularization go to 0. And in fact, we even want to kind of identify in a unique way a limit. That can also be done, but that's not part of this course. And so just to give you an overview about the next week, so probably I will go back a little bit to some of these points which I glossed over here, but most of them are in the script, which should have been posted this morning. I mean, the new version of the script. Then, in fact, we'll prove a more general result. So we will not just look at Gaussian ensembles, and we will replace this condition here by what's called a spectral gap condition. And in fact, we'll use Malliavin calculus to derive these estimates. So that's the kind of, after all, the second part in the title. So the regularity structures I now explained in the first week. And in the second week, I hope to explain to you how this Malliavin calculus is a very natural and convenient tool to get exactly these stochastic estimates. So that's happening afterwards. So let me stop here. Perhaps you still have some questions, but I think it's almost time for coffee break. Questions? Yes.
I mean, in your lecture note, the SE specifies the scale of invariance in log.
Yes.
And when S equals 0 is the white noise?
Yes.
So your theorem doesn't apply to the white noise?
So it does not apply to the white noise for two reasons. So I think I didn't state this here. So we're looking on Schwarz distributions on the space 1 plus 3, right? Sorry, 1 plus 3. We're looking at the case when the space dimension, when space-time dimension. Yes, we're looking at this case. So that was this choice of d equal to 6. Now I'm confused. So now that's 1 plus 4. Sorry, little d is equal to 4. So that's a famous situation. Kind of the four-dimensional case is the case of 4 space dimensions is absolutely critical for these 5-4 models. And in fact, there is a famous result by Eisenman and Dumesnil-Copin who show that in this case, you cannot successfully renormalize. Whatever you do, you get something trivial. So that's a hard reason for excluding, in this specific situation, the case of s equal to 0. Then there is a soft reason for having to exclude it, even if we were to go in 3 dimensions, and that has to do with our method, which is based on Liouville. And because we want to use this Liouville principle, we need, or it's convenient to have that S is irrational, because that allowed us to apply this PDE statement. So there are kind of 2 reasons, one crucial in this dimension, and one more technical, to actually rule out white noise. There is a way of kind of, let's say in the case when d is equal to 3, when there is no fundamental problem, there is a way of dealing with this by kind of treating white noise as something that's slightly worse and performing a large-scale cutoff. And then you can embed white noise into this theorem. But the short answer is no, it does not include white noise. Yes?
So I have a question about the transitioning band, the gamma.
Yes.
Does this map depend on lambda, or is really just translation for all lambda?
So kind of on the informal level, it was something which for a given lambda in a given analytic function p associated again the lambda in the first coordinate, and then a p which depends on lambda and the base point x. So it's a nonlinear map which has a triangular structure in this sense. And the translation on the level of gamma was that the Z3 variable is trivial. So in that sense, there is a lambda dependence of this map, but not a direct lambda dependence. It's an indirect lambda dependence because these multi-indices will have a component in the 3. Will have a 3 component.
Yeah.
Right? Also here, the reason is that this depends on lambda, right?
So we can really consider it as a dual map of translation only when lambda equals to 0, and in another case, it just has some properties which similar to the translation map, right?
Well, so informally we said there must be a way of writing the Q as a function of lambda and p, right? And this function we call p lambda x, right? So that's an informal statement. We algebraize this with help of this map gamma x. That can be rigorously constructed. So it's very much like the model itself. We didn't really construct this this object here, but we kind of lifted it into the term-by-term world, in the world of formal power series, and there the coefficients can be rigorously constructed. And the same spirit applies to this transformation. So after lifting these objects, it's good to develop an intuition, a geometric intuition as I did, but then you have to realize that you cannot carry this through. Instead, you have to kind of algebraize it, lift it to in this term-by-term world of formal power series, And then these objects can be constructed, can be estimated, you can pass to the limit in those. More questions? One question? Otherwise, I think it's good time for coffee. Let's pass to coffee.